Right, so over the last 4 sessions we've been looking at specialist training methods, what they are, how they work, the physiological benefits in particular reference to certain sports, certain individuals. But ultimately if we leave our planning there, then we are missing a key ingredient of effective training program planning, and that is to establish, to identify whether the methods we're putting in place are having the desired effect. So over the next 2 sessions, we're going to be looking at fitness testing, 4 key methods in particular, 2 in this session, 2 in the next. And we're going to start with the simplest one of the lot, and that is lactate sampling. Now, lactate sampling requires taking a small amount of blood, literally a pinprick of blood. And it's often taken from the lobe of the ear or the fleshy part of the thumb here during the session or immediately after the session. And the test is designed to identify the amount of lactate present in the blood. Now, that tells me 2 things really, or always useful to me in 2 ways. First thing, it can tell me how hard I'm working. So if I've got a high level of lactate within the blood, then clearly I've been working at a moderate to high intensity. If there's an absence of lactate in the blood or a low level of lactate within the blood, then clearly I've been working at a low intensity. Now that's quite important because actually I might be at a point within my training program where I need to be working at a moderate to high intensity. The session may demand that I should be working at a moderate to high intensity. But if the lactate sample shows that there's an absence or a low level of lactate, then clearly I've got to be working harder. Important for the coach to monitor that as well. But similarly, I might be at a point where I'm tapering towards a major event as part of my macro cycle. And actually the intensity of exercise needs to be quite low. So lactate sampling can be important in this point because if lactate levels appear too high, then clearly I've got to slow down a little. I've got to lower the intensity. So that's one way in which we can use lactate sampling. A second way is that we can monitor improvements. So if I've set out my program and I'm running a series of sessions over 2 to 3 weeks of similar intensity, then I can monitor whether those sessions are having the desired effect. So if I lactate sample at the beginning and then I lactate sample maybe session 6, I should see if my training program is working that the lactate concentration is less in that sample of the 6th session compared to the 1st. That shows me that my aerobic energy system is improving. I'm delaying the onset of blood lactate accumulation. That will tell me I'm delaying my lactate threshold, and knowing the relationship as we do now between the 2, that's going to show that my VO2 max is improving. So ways in which that's important to us to know. Thing about lactate sampling, it's accurate, it's objective, so it's an ideal measurement to recognise whether our method is working. So that's lactate sampling. The next one is a little bit more complicated, and it's known as respiratory exchange ratio, RER for short. Now this is focused primarily on the nutrients we are using to produce energy, so namely carbohydrates, fats and proteins. Now we're going to leave proteins out. We're not going to bother with proteins. We're just going to look at fats and carbohydrates in this session. Now the inherent chemical differences in the composition of carbohydrates and fats means that different levels of oxygen are required to oxidize the carbon and hydrogen atoms within those nutrients to essentially produce carbon dioxide and water, as well as release the energy from within. And what the respiratory exchange ratio does is it measures the amount of carbon dioxide produced compared to the amount of oxygen that's been consumed in that chemical reaction. So if I give you an idea and we look at carbohydrates first, what respiratory exchange ratio attempts to tell us is to estimate that within our activity, within our session, how much are we relying on carbohydrates and how much are we relying on fats as a key nutrient to support the energy needs of that activity. And that's quite important. We'll come to that in a second. So let's just start with carbohydrates. If we look then at the chemical formula of carbohydrates, we have 6 carbons, we have 12 hydrogen atoms and 6 oxygen atoms. Now, because the ratio between the hydrogen atoms and the oxygen atoms are 2 to 1, the same as in water, this means that all the oxygen consumed when breaking down, when oxidizing the glucose molecule, all of that oxygen consumed goes to produce carbon dioxide. So 6 oxygen molecules will produce, in the breakdown, 6 carbon dioxide molecules. So our ratio, our respiratory exchange ratio, and we always start with carbon dioxide first, means that we have 6 carbon dioxide molecules produced compared to 6 oxygen molecules consumed. 6 oxygen molecules used. Now we can simplify that further, obviously, 1 to 1. And actually now we can take that all away because our figure is 1. 1 divided by 1 is 1. And that figure is really important because if the result of my respiratory exchange ratio test is 1, I can tell that my athlete is actually relying on glucose, relying on carbohydrate as the key nutrient, the key energy support for that particular activity, the key energy source. All right, that tells me something about intensity. We'll come back to that in a second. So that's carbohydrate. Now, if we look at fat, fat's a little bit different. So within fat, there are 16 carbon atoms. There are 32 hydrogen atoms, but only 2 oxygen atoms. So the lack of oxygen within the molecule, the disproportionate spread here, if you like, means that actually, as I've said before, fat requires a much higher level of oxygen in order to break down. A much higher level of oxygen is going to be required in this chemical reaction to provide carbon dioxide, to release the energy within the fat molecule and to provide carbon dioxide. And as proof of that, 23 oxygen molecules are required in the catabolism, the breakdown of fat, to produce 16 carbon dioxide molecules. Okay? 23 oxygen molecules are required to oxidize the carbon to produce 16 carbon dioxide molecules in the chemical reaction. So again, if we look at our respiratory exchange ratio, starting with the carbon dioxide first, that's 16 carbon dioxide molecules produced in the chemical reaction compared to 23 oxygen molecules used or consumed within that chemical reaction to release the energy. Now, we can't really simplify that further, but we do as we did in the last one. We're going to divide the carbon dioxide figure by the oxygen figure, and that gives us a figure of 0.7. So if we see at the end of our respiratory exchange ratio test a figure of 0.7, that tells us that the performer, the athlete, is relying on or has a greater reliance on fat molecules as an energy source compared to carbohydrates. Okay, so there's a greater reliance on fat. Now this is really important here because, as we've shown already, and I've said in the past, but hopefully you've seen here, in order for fat to be catabolized, in order for fat molecules to be broken down to provide energy, they require a huge presence of oxygen. Fats contain far greater energy potential than carbohydrates, but as a result, it requires an awful lot of oxygen to break it down, which means we only really use fats in lower intensity exercise. So if an athlete, if a performer has a figure of 0.7, it means that they're reliant on fat as an energy source. It means that they must be working at a lower intensity. You cannot catabolize fat. You cannot break down fat to provide energy where there is low levels of oxygen. So they cannot be working at moderate to high levels of of intensity. So if we do a kind of a sum up of that, so if my RER is close to 1, that tells me that I am using carbohydrates as a main source of energy. That tells me, because essentially I'm using the same amount of oxygen to produce the same amount of carbohydrate, that actually I can be working at a moderate to high intensity. That's what that tells me. If I have an RER of 0.7, that tells me that actually fats are the main energy source in this situation. Now, because I know I require high presence of oxygen in order for fats to catabolize, to break down, to produce energy, it means I must be working at a low intensity. And if you look back at what we said about lactate sampling, the same things apply. So by using a respiratory exchange ratio, I can tell if we're working hard enough. I can also monitor my performance, my progress, because actually if we look at marathon runners have essentially adapted their bodies through their process of training to use fats as a source of energy over carbohydrates. They're far more adept, their bodies are far more adept at processing and breaking down fat for energy that gives them that extra energy source. So those are the first two fitness tests that we're going to look at. 2 more to come.